The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome to 1690. I'm Professor Qiqi Wang, and this is Professor Willcox. So we are going to be together teaching 1690 this year. So 1690 is Introduction to Numerical Methods for Engineering, Aerospace Engineering. And so what I'm going to do today is you're going to see this weird device. Some of you have seen downstairs this all the time. I don't know what it is. I will tell you what it is today. But before that, let's go over about what this class is about. I want to show this. All right. Okay. So I'm going to first go over the syllable, and then Professor Willcox is going to show you something new this semester that is very exciting for you to actually a great way to guide yourself to learn the material yourself. Because this lecture is really, this class is really taking advantage of the inverted classroom structure. We really want you to learn the material before you come to class. And in class, we are going to be assuming you have read the material and we are going to be solving problems together, right? So this is really not a new style. This style has been like practiced in this department for a while. So lecture 1. We are not using computers to do a lot of things. Every of you are using computer checking emails and things like that. But computers are first invented to do numerical simulations. Okay, the reason we have computers is because of things we are going to be talking about in this class. So the first real computer is designed not for checking emails, but for computational simulation to help engineers solve problems in ballistics. And these are really aero problems. So we are going to see something very similar to the world's first computer application in this subject. Okay, so let's fast forward in time and come to today. Today, computer simulations haven't become less important, but increasingly important for studying, interpreting, and predicting many different processes. And we are in aerospace engineering, so I'm just going to be talking about some aerospace examples, but like outside aerospace, you can find even a lot of broad applications of computational simulation. So this is a class, even though you not end up doing aerospace, it is going to be also extremely useful. As long as you do something related to either science or engineering, this is going to be useful. So two examples are simulation of spacecraft re-entry, and this is the real thing. This is the simulation. Another example, designing next-generation hypersonic vehicles. This is the real thing. This is the simulation. And we are going to be talking about how to perform this kind of simulations. And these are PDs because you have multiple spatial dimensions, where you have X, Y, and Z. And if you are unsteady, you also have the fourth dimension, which is time. So to solve problems using numerical methods, solve problems like that, it really involves two steps. So this subject, we are going to be spending a lot of time talking about how to solve differential equations. But let's not forget the first step. That is how you would actually get these differential equations. Okay, so the first step really is to reduce a real system of process of inputs into a mathematical model. And in a lot of times, you are going to find out the mathematical model is going to be a differential equation. So to figure out what kind of mathematical model is suitable for the system of process you are interested in, you have to first know what are the quantities of input. Like in a system, what do you want to know? Okay. And what are the key processes involved? What approximations can we reasonably make that is going to lead you to the right prediction of the quality of interest? And the model we are going to derive once you go over the steps can be differential equations, statistical models, it can be linear or nonlinear. If you look at the measurable outcomes, distinguishes between linear and nonlinear equations is one of these. Okay, it can be deterministic or probabilistic. At the end of this subject, we are going to be looking at probabilistic simulations. It can be static or dynamic, which involves time or doesn't involve time. It can be discrete or continuous, either based on first principle, conservation of mass, right? Conservation of momentum, conservation of energy, or empirical, with regard to some empirical relationship and use that simulation. And once you have that, you define the computation code to solve the mathematical model. So let's take a look at an example of computational modeling. The model is a thermal problem. So this is really, this guy is a transient thermodynamics problem. Problems like this is important in gas turbine engines when you have something spinning up. Once the different parts are going to heat up at different rates and expand at different rates. You want, during the entire process of different parts expanding at different rates, nothing is going to hit another part, right? You don't want the spinning compressors or turbines, which actually expands, heat up faster than the outside of the turbine engine to actually hit the outside case. So you need to really predict well how fast different parts are heating up during the process. So our model problem is this. This is the aluminum. It's 3.89 centimeters cubed, initially at room temperature. It is going to be heated up by this heat bomb, okay, starting at time equal to T0. We're going to be turning off the hot air at time equal to T1. So here comes the quantity of input, the measured temperature. So you see here, it's a thermocouple, basically stuck inside the center of the aluminum tube. And we have a USB cable. We're going to be kind of seeing how this thing heats up. So what I want you to do is to form a team of either 2 or 3. Okay, look at the neighbors, commit to a team. And also these questions. I've already given you what is the quantity of interest, the temperature in the middle of the cube. Now the question is, what are the important physics involved? And how to model the physics mathematically? Okay, and the last, I'm actually going to show you, because this is what we're going to be learning in this class, how to use the mathematical model to make the predictions, which means how to solve these equations we come up with. So, form a team and start with these 2 questions. At the same time as you form a team, I'm going to start this whole thing. Last time we actually had more time for you to solve this. So this time we are running out of time. But like I know a lot of you haven't got to the bottom yet. But like a lot of you, I think given more time, it's going to derive the equations. Especially some of you are looking up online and taking a lot of time to calculate. So here I think I'm just going to wrap up by telling you how I would model it. There is no single way of modeling this, but like my way is just a, you see, insert after, yeah. Okay. All right. So, what is the physical process that determines the quantity of interest, which is the temperature of the cube? I'm saying the temperature of the cube because aluminum is very good conductor of heat. So if there is unevenness in the temperature distribution inside the cube, it is going to even out very fast, especially for a cube of this small size. All right. So one can assume that the temperature distribution inside the aluminum is basically uniform throughout. When you look at the time history, it heats up so slowly over like a course of many minutes. The temperature, the conduction inside the aluminum is actually much faster than that. So we can say that the temperature, oh, I don't want this color. Okay, the temperature of the aluminum is only a function of time. Okay, so this is the temperature of the cube. Okay, now we have the temperature of the cube. So what governs the temperature of the cube? What makes the temperature of the cube change? Heat convection. Okay, so we have heat convection. Okay, we had heat convection that makes the delta of the internal energy of the cube, right, equal to what? So let's say that the between two time points, the change of the energy of the cube is equal to what has contribution to the energy change. Yes, what I'm looking for is the change in the energy is really equal to the heat that goes into the cube plus work done to the cube, right? And nobody did any work to the cube, right? I didn't. I don't know if you did, but like so it is only equal to the heat convection into the cube. All right. So this is how you start putting the physical process into equations. Now let's look at how do we relate both sides of the equation to the temperature of the cube. Okay, how do you relate the delta in the internal energy to the temperature of the cube? So the change in the energy relates to the change in temperature, right? How does it relate to the change in temperature? Delta T times what? Cp times the mass, right? Okay, and the mass, we although we don't know exactly what it is, we can look up for the density of the aluminum and the cube of the diameter of the size of the cube, right? So this is going to give us the change in energy, and what determines how much heat has convected into the cube? The left hand side. So okay. So I think I should write like this. What determines Q? What determines the heat that goes through the surface of the cube into the cube? Good. So that is Q from the gong minus Q. So this is gong to cube, right? So this is cube to air. So this is gong to cube minus cube to air. Now, how do you model? How does the rate of heat transfer from the gong to the cube depends on the temperature? And how does the heat convecting from the cube to the air depends on the temperature? Yeah, they linearly depend on the difference in the temperature. So if you look back on your unified notes, okay, so these are heat convection, right? Heat convection, and when you blow air from the gong to the cube, it is forced convection. Okay, so this is the rate of the forced convection. It is proportional to the temperature of the hot air minus the temperature of the cube times the coefficient, and the coefficient is the forced convection coefficient in the air times the area of the convection. And for example, otherwise it may not be very speaking from the back. We can assume we are just heating from these two sides. Okay, so maybe we can just say 2 times d squared is the temperature of the heating, and maybe the cube to air is C free convection times now 4 sides of free convection. Now it's T minus T air. All right. And this is the rate of heat convection. Now we times the delta of time. We are going to get the amount of heat that went into the cube during a small time unit. Now this is going to give us a differential equation, because if we let the delta T, the amount of time we are looking at, goes to 0, we are going to get the equation of Cp times rho d cube of dt dt. So this is the rate of change in the temperature, equal to C force times 2d squared th minus T minus C free 4d squared T minus T air. Right, so this is the differential equation we get. Now, what changes when we turn off the heat gun? C force is gone and the C free becomes 6 size. Right, so that's the difference. And let's go to MATLAB. And I wrote a code for simulating this. So here's the parameters. Ambient temperature, we said today is a little bit colder than I thought. And the hot air temperature, if we look at this, I think it's like 106 or something. Let's put 106. And the start time in seconds, I actually don't know. So let's just put 0 here. And the T-stop in seconds, what time is it? Like 11 minutes? What is 11 minutes in? So this is 11 minutes, right? Okay. T-end, I think I'll just do this. Okay, so these are what I looked up online. Some of the values for the free air convection and forced air convection, and the size of the aluminum cube, the density of the aluminum, and the specific heat capacitance. All right, and these you don't need to look at them because they are never used in the code. Because radiation is actually not important. So heating, and we are using forward Euler to solve the equation. I'm basically saying that the heating rate is proportional to 2 sides, and the cooling rate, and etc. And we are also doing the cooling. So let's do the simulation. We are getting a plot like this, and let's compare our is it temperature.txt? Thought I added temperature.txt. Oh, okay. I need to get rid of these. Let me first stop. Not responding. Error writing. Come on. Close the program. All right. Okay. Now we are plotting. So look at the difference between the simulation and the experiment. It's huge, right? So what is causing this difference? It is because now here what I said is the force convection coefficient is 10 watt per meter squared per K, right? Now let's go to internet and search for forced convection coefficient of air. Engineering toolbox. Is it this one? Yes. Forced convection of air. It goes all the way from 10 to 200. Okay, and here I'm actually putting the lower bound. If I put something like 200 and do the simulation again, and do the experiment again, this is what I got. Okay, it got a much better match, and also I also have my free convection to be 5. If you look over the internet, free convection goes from 5 to 25. Okay, and I also so if I go to 25, I think I am also going to be getting much better match. Okay, so the rate of decaying is much better now. And another thing I assumed is only 2 sides of the drum, 2 sides of the tube is being heated and 4 sides are radiating. But actually, if you kind of solve a fluid mechanics problem, you are going to be finding more than 2 sides are being heated. So that is actually another motivation for why we need to look at not only one simulation, but an ensemble of simulations. And that is relating to the fourth part of this subject, probabilistic simulations. Because when you look at a lot of physical phenomena, there is a lot of uncertainty in it when you look at the range of coefficients you can possibly get in modeling physics. And convection is a prime example of this, because there are so much uncertainty in what rate you can get. All right, so this is our first lecture. I'll see you next Monday. But remember, one thing is you need to read and do the homework, do the embedded questions before you come to class next Monday.